So this afternoon we're going to look at work, energy, and power. Okay. One of the things we're going to learn is what work is, what do we mean by energy, and also how do we define power. Okay. Of course, other things are going to be introduced of importance is something called the work energy theorem. This is very, very important, and also something called conservation of energy. So work energy theorem is basically a connection which you're going to see which exists between how much work a person has done and how much energy is transferred to that particular object or that particular person. You will learn how do we define work in physics, what do we mean by work, and when do we consider work to have been done. And you also learn to how to calculate work in a couple of situations, and basically in a nutshell, what does it mean? What are the implications when work has been done? What does it mean when you do work? Okay, so basically the one thing you're going to learn is that when you do work on a particular object, you transfer energy from yourself, the person who is doing the work, to that particular object. That's basically the thing about work. When you do work, you transfer energy from you, the person who is doing work, to that particular object. So you're going to look at a couple of examples of how work can be done and how much work is actually going to be done. Then next we're going to look at types of energy, kinetic energy, gravitational potential energy. But the most important bit about energy is that all the energy which we use on this earth actually comes from the sun. Okay, so what we actually do are basically clever engineering ways of either capturing that energy or converting it from one form to another. Then that is going to bring us, the conversion of energy from one form to another is going to bring us to something called conservation of energy, meaning that you cannot create energy and you can't destroy it, but energy is simply changed from one form to another. So in other words, what we are saying is that energy has got many faces. That's what we mean. There are different forms of energy. Each of these forms, with the right kind of engineering, and some of them with very little or to no engineering, very, very little, you can change from one form of energy to another. Then last but not least, of course, is something called power. Power measures how fast you are doing work. That's what power is, how fast you are doing work. And remember what work is. Work is you transferring energy from one point, from yourself to another body. So how fast are you transferring this energy? That's what power is. So we'll look at an expression of power, but of course of interest is this other expression where power is defined as the force multiplied by the average velocity of that particular object. So you have to move an object in a way. Okay, so let's start with work. Now in physics, we define work using force and displacement. Okay, two things you need to be aware of. There has to be a force and there has to be a displacement. A displacement in the sense that when you perform work, you need to be able to move an object from point A to point B. If that particular object does not move, then there is no work which has been performed. Okay? When it comes to the force, we are interested in the force which lies along the direction in which the object is moving. So your force might be pointing in a particular direction, your object is moving in a particular direction, but the question is how much of this force lies along the direction in which the object is moving. How much of the force lies along the direction in which the object has moved. So if an object moves from point A to point B, the reason why it has moved is because you applied the force. What we want to find out is how much of this force is in the same direction as the displacement. So it is this force you are interested in. This force, the component of the force which is in the same direction as the object which is moving, multiplied by the displacement. That is what gives us work. So here we are trying to define work. We're saying the work is equals to the component of the force along the direction in which the object has moved multiplied by the displacement. So this component of the force, we're actually calling it the x component of the force. And how do you get the x component of a force? The fx is equals to the force multiplied by the cosine of the angle between that particular force and the direction in which the object has moved. So when it comes to work, eventually when you work out what this is, when you figure out what fx is, which is equals to f cos theta, here f cos theta multiplied by the displacement, which is h. So you end up having work to be equals to the force multiplied by the displacement multiplied by the cosine of the angle between the direction of the force and the direction in which the object is moving, where F is the force you're exerting, so you need to apply a force on an object. Then the displacement is the displacement you need the object moves, and the angle theta is the angle between the force and the displacement. Why that angle? It is because we are only interested in the force which lies in the same direction. We are only interested in the part of the force which lies in the same direction as the direction in which the object is moving. Are we clear on what work is and how do we find it? Is it clear? The force, we are interested in the part of the force which is in the same direction as the direction in which the object is moving, F cos theta, which is the x component of the force, multiplied by the displacement, and that is what gives you your work. This work, we are multiplying force multiplied by displacement. So this work has got units of newtons, meters, and that Newton meters, 1 Newton meter is basically what is called a joule, named after James Prescott Joule, who was a British scientist. Okay. A couple of things you notice here about work. If the object does not move, if S is equals to 0, if your object does not move, then the work done is equals to 0. It doesn't matter how much you push or how much you pull. If the object does not move, then the amount of work you have done will be equals to 0. Here, if S is equals to 0, then this whole thing becomes equals to 0. Are we clear? Is that clear? Okay, so for you to perform work, an object actually has to move. If it doesn't move, then the work done is going to be equal to 0. The other thing is here, there is a theta here. If the force and the displacement are pointing in the same direction, if this force F and this displacement S are pointing in the same direction, then the angle theta is going to be equal to 0. So you end up having theta equals to 0. When theta is equals to 0, the work you're going to do, W, is equals to F S cos 0 degrees, which is going to give you this, Fs. This is the work you're going to do. This kind of work, which is just Fs, this is what is called positive work. Why do we say it's positive? As you are going to see, in the next case, you can have work which is equals to 0 or negative. Okay, so if the force and the displacement are pointing in the same direction, then this is how much the work is going to be, Fs, because this angle between the force and the displacement is going to be equals to 0. If, on the other hand, the force and the displacement are at 90 degrees to each other, the object is moving in one direction, but the force is at 90 degrees to the direction in which the object is moving, 90 degrees to each other. In that case, as much as the object is moving, there is no force or there is no work which is done by the object. So if you assume that the object is going to move this direction, then at 90 degrees, then the force is going to be applied at 90 degrees to the object, then there will be no force done here. So the work done is going to be, so if there's going to be no work done, the work done is going to be 0. If, on the other hand, the force is opposite the direction in which the object is moving, meaning that the angle between the force and the displacement is 180 degrees. If the force is opposite the direction in which the object is moving, the angle is 180 degrees, then what you're going to end up with is minus Fs. So here you see a minus sign, a negative sign. This means that the work is negative. So you see a couple of things here. You can see that work can be positive, work can be equals to 0, depending on the angle. If the angle is equals to 0 degrees, if the angle between the force and the displacement is equals to 0 degrees, then in that case the work is positive. If the angle between the force and the displacement is equals to 90 degrees, the work is equals to 0. If the angle is between the force and the displacement is equals to 180 degrees, in this case the work is negative. So you can have positive work, you can have 0 work, you can have negative work. The question is, what does it mean if you perform positive work? What does it mean if you perform 0 work? What does it mean if you perform negative work? Well, the meaning is that if you perform positive work, then this positive work is going to result in the transfer of energy from the object applying the force F to the object which is being moved by the force through a displacement x. So if you are the one pushing an object, or you are the one pulling an object in the same, like when you're pushing, when you push an object, that object is moving in the same direction as the force. So in this case, when you're pushing an object, you are transferring energy from yourself, who is pulling or pushing the object. You're transferring this energy to the particular object you are pushing through a distance s. So positive work results in the transfer of energy. The object being pushed or pulled gains energy. Are we clear? Is it clear that when you perform positive work, the object you are pushing or pulling is going to gain that energy? The energy which is going to be gained is going to be equal to the work that has been done. Is that clear? When you perform 0 work, if you have done 0 work, it's like the way you're doing the way you write your exams. You study very hard for a particular exam. Then if your results are positive, you have increased your results, then fine, you have worked positively. But if you study, but your result is still the same as last time, you have performed 0 work. Okay. So when you perform 0 work, 0 work results, 0 work means that there is no transfer of energy from the force to the object which is moving through a distance s. So if the work done is equals to 0, it means that the object which is being moved through a displacement s does not gain any energy. When the work done is positive, it means that that particular object gains energy. When the work done is negative, it means that energy is lost. The force does not transfer the energy, but what the force does, it gets energy away from the object. It gets energy. Negative work means that the energy is not transferred to the object, but instead is removed from that particular object. So when a force does negative work, this negative work results in energy being lost from this particular object. Is that clear? Yes. So when you do positive work, you transfer energy to the particular object. When you do zero work, you don't transfer any energy. When you do negative work, you remove energy from that particular object. Here are a couple of examples. A force of 3 newtons acts through a distance of 12 meters in the same direction as the force. Find the work done. So in this case, you've got a force acting of 3 newtons, and this force causes a displacement of 12 meters in the same direction. So the work done, of course, as you have said, work is equal to the force you have applied multiplied by the displacement multiplied by the cosine of the angle. Okay, so since the direction is the same, the displacement and the force are acting in the same direction, then the angle between these guys is 0. So the work done will be 3 newtons multiplied by 12 newtons multiplied by the cosine of the angle, which is 0 newtons. Cos 0 is 1, so you end up having 3 newtons times 12 newtons, which is equals to 36 joules. This 36 joules means that this is the amount of energy which was transferred as a result of this work. Are we clear? So that is in the same direction. Okay, next example. An object is being put along the ground by a 75 Newton force directed at 28 degrees above the horizontal. How much work does the force do in pulling the object 8 meters? So again, the force which is being applied is 75 newtons. The angle between the force and the direction in which the object is moving is 28 degrees, and the displacement or the distance through which the object moves in a straight line is 8 meters. So in this case, the work done, how much energy is going to be transferred, work done is going to be equal to the force multiplied by the displacement multiplied by the cosine of the angle. So in this case, you have a force of 75 newtons here, then the displacement is 8 meters there, and the cosine of the angle is cos 28 degrees, and you end up having work of 530 joules being done. So this is how much work is going to be done. So you clearly see work depends on how much force you're applying. It also depends on the displacement or the distance the object has moved, and it depends on the angle in which the object has moved. Okay, another example here is 0.3 kg object slides 0.8 meters along the horizontal table. How much work is done overcoming friction between the object and the table if the coefficient of friction is 0.2? So in this case, the object slides through a distance or a displacement of 0.8 meters. And because of this sliding, there is friction. Friction is always acting opposite the direction in which the object is moving. So we have the mass, which is this one, and we have got the coefficient of friction, which is 0.2. So we can use this to work out what the friction force is, because we need to find out what the friction force is. Since the object is moving, so we're talking about coefficient of kinetic friction, which is 0.2. And these are the typical values of the coefficient of kinetic friction: 0.2, 0.3, 0.25, or 0.15. So the friction force, how do we get friction? Friction is equal to the coefficient multiplied by the normal force. So the friction force is going to be equal to the coefficient of friction multiplied by the normal force. However, the normal force, we know the normal force from our discussions when you're looking at Newton's second laws of motion, the normal force is equal to the mass of an object multiplied by acceleration due to gravity. So in our case, the normal force is going to be equal to the mass of the object, which is 0.3 kgs, multiplied by 9.8 meters per second, and we get a normal force of 2.94 newtons. This normal force, which you have here, we multiply it by the coefficient of friction. It's going to give us a friction force. So that's going to be here the coefficient of friction multiplied by the normal force. So we end up having 0.2 times 2.94 newtons, and that gives us a friction force of 0.588 newtons. So this is the friction force acting on the object. However, what we know is the friction force is opposite. It opposes motion, so it acts in the direction which is opposite to the direction in which the object is moving. So we can work out, so the angle between the friction force and the direction in which the object is moving is 180 degrees, because friction is always opposite. In that case, the work done is going to be equal to the friction force multiplied by the displacement, which is 0.8, multiplied by the cosine of the angle, which is 180 degrees. So the friction force we have found is 0.588 newtons, multiplied by the displacement, which is minus 0.8, then multiplied by the cosine of the angle, which is that cos 180 degrees, which will give us a negative. So we end up having the work done being equals to minus 0.47 joules. So this is how much work is done, or basically this is how much energy the object is going to lose as it slides to a stop. Are we clear? Is it clear?
Yes, it's clear.
Yes, on how you work out work when the force and the displacement are in the same direction, when there's an angle between these, like in the case of 28 degrees, and also when the force and the displacement are opposite each other. Okay, here is another example of how you work out work. Now this case, you're doing work against gravity. So how much work is done against gravity in lifting a 0.8 kg object at constant velocity through a distance of 0.4 meters? Now, there is a force associated with gravity, which is the weight of an object. So when you ask you to find out how much work is done against gravity, there is a force associated with gravity. So if you're lifting an object, and you're lifting this particular object at constant velocity, then it means that there is no acceleration. In that case, what it means is that the force of lifting, the lift force, and the weight of the object are the same. And in this case, it's mg, which is, since there is no acceleration, there's a lift force lifting the object up, there's gravity, which is the weight pointing down. These two are the lift force and the gravity. The net force is equal to 0, and if the net force is equal to 0, then it means that the lift force is equal to the weight. So that's the lift force. So in this case, the lift force is going to be equal to 3 kg multiplied by the acceleration due to gravity, which is 9.8. This part here is just the weight of the object. But what we are saying is the weight of the object is equal to the lift force. That's what they're saying, since the object is being lifted at constant velocity. Okay, so we end up having a lift force which is equal to 29.4 newtons. Now, since you're lifting this object, meaning that you're pulling it up, and the object is coming up with you as you're pulling it, the displacement is 0.4 meters. Therefore, it means that the lift force and the displacement are in the same direction. So this here, so we say the work done is going to be equal to the lift force and the displacement times the cosine of the angle between these two. Of course, the angle is the same, is 0, because the lift force is pointing up, the displacement is also pointing up. So in that case, this angle theta is equal to 0. So the lift force is 29.4 newtons. The displacement, which is what you have here, the displacement is 0.4 meters, like that, and the angle between these guys is 0 degrees. So we end up having the work done being equals to 11.8 joules. So this, when you lift an object, when you are lifting an object, as you can see here, that particular object, when you're lifting an object, you are performing positive work. And that particular object you're lifting is going to gain the energy which is equal to the amount of work you have done. So the point is, when you do work, one of three things are going to happen. If the work you have done is positive, that work is going to result in energy being transferred to the object on which you're doing work. If the work you have done is equal to 0, then there's no energy which is going to be transferred. If the work which has been done is negative, then that work is going to result, the work you're going to do is going to result in energy being removed from the object which is in question. Is that clear? Are we together? Okay. So that's basically about work for now, but we're going to come back to it later because we need to introduce another thing called energy. Now, the one thing I want to mention is, as much as you take the sun for granted, because it comes every morning, you expect to see it, it's there. The sun and the energy we get from the sun is the reason why life is possible on Earth. We receive all our energy from the sun, which of course happens to be our nearest star. So if you're not aware that the sun is actually a star, now you're aware. So the thing really is, for you to have life, and for you to have life you need energy. For you to have life and for you to sustain life, you need energy. You need the sun. Without having a sun, life won't be possible. Okay. So the sun, the energy which comes from the sun every day and across the year we receive a lot of it. Some of this energy is captured by plants through photosynthesis. Some of it is captured by algae which live in water, and these algae, they have chloroplast in them. The energy which they have through this chloroplast which they have, chloroplast is available in plants and also in these algae. So there are a lot of these algae in our oceans, in our lakes. So they capture this energy through photosynthesis, and when they capture this energy, they store this energy in the form of chemical energy. So the energy from the sun, when it's captured, it's stored in the form of chemical energy. This chemical energy is basically, we're talking about carbohydrates, or you're talking about proteins, or you're talking about fats. Okay? So these chemicals, these chemical compounds, carbohydrates, proteins, and fats, as you are going to study your chemistry and biology, you will learn that proteins, carbohydrates, and fats are actually chemicals. Okay? And these are the things we actually eat as food. So we eat different types of carbohydrates. For example, in Zambia, we are used to eating inshima, or whether you eat cornflakes, it's still a carbohydrate. If you take milk, that's a carbohydrate. If you eat meat, that's a carbohydrate. That's a protein, and it's a compound. Fats also. Okay, so, and how do you get these things? Yeah, in a carbohydrate part, maize is straightforward, but also you can get your proteins, let's say for example from beans or soya beans. So those are source of proteins. But you also have a case where maybe a cow eats some grass which had captured this energy. So the cow eating grass, it gets this energy it captured from the which was captured by the grass, and it turns into milk, or it turns into meat, and you end up eating that particular meat. In the case of let's say for instance pigs, you create feed from your maize, your carbohydrates, and that feed is used to feed the pigs, and the pigs become fat, and you end up getting bacon or whatever it is you're getting from these animals. So the point really is that the energy from the sun gets captured by plants, and these plants are eaten by other animals like human beings or cows or goats or pigs. So the energy which was captured gets transferred to these animals. Okay, then from your cows you get your milk, so you get your proteins, or you get whatever it is you have to get. So the energy you're basically getting is what's not, it's a form of energy you get from, the energy you get from food is a form of energy which is called chemical energy. And as you are aware, it's very important that you have your breakfast, you have your lunch, and also you've got your supper. If you don't eat, you can't live. You very soon you'll die, okay? Because it's not possible for you to live without energy. You need a form of energy, and that form of energy comes to us in the form of food. So what you're getting from the food is basically chemical energy, and you can clearly see when you, I think you felt it, when you've eaten, you eat, then you're full, then you're feeling rejuvenated. But of course, that energy you get from your food is not going to last, because one, some of that energy you get from your food, you're going to use it to keep your body temperature. Your temperature of your body is at a certain temperature, and for you to do that, you need energy. You walk around, and walking takes energy. It's a tiring process. So as you are doing all these things, as you go about doing whatever things you do, you will be spending your energy. The energy you got from your food, you will spend it. Even if you just lie in bed, you eat your breakfast, then you just lie in bed without doing anything. The fact that you're just there in bed, that also requires energy, because your body needs to keep a certain temperature. For that temperature to be kept, it needs to burn the energy which you have, which is stored in your food. So eventually you will get hungry and you need more food. Are we clear? And this, your body will tell you, would say, no, we need food, Onga, because it tell you, hey, you're hungry, Onga. If you don't want to eat, it will start making all sorts of noises. But basically, the point here is the energy you get from your food actually came from the sun, because a plant captured that energy, then that plant was eaten by something, by a cow, then you got your milk from there, or a chicken, you got your eggs from there, and stuff like that. So life is not possible without the sun. Are we clear? Without the sun, life can't happen. It's not possible without the sun. Okay? The sun is also the other thing which makes it possible for us to have rain. Because of the evaporation, then the water rises up into the sky, then it forms clouds. Eventually that water falls somewhere as rain. And it's that rain which falls in rivers, that's what we use for making electricity. So without rains, which are caused by the sun, you would have no electricity. You would not be able to cook. You won't charge your phone. Basically, everything will come to a standstill. Last year, we had the experience of what happens when you don't have electricity in a country. Literally, everything comes to a standstill. Are we clear? So you need energy. At least even if you don't have electricity, but you need food. Because without food, which is the source of your chemical energy, you will not be able to live. You will die. Okay. So, we have looked at one form of energy, which is chemical energy. And if you have a packet of whatever it is, whether it's milk in your house or it's anything, if you look at the nutritional table of your food, the first item on that nutritional table is how much energy you get from that food. Okay? So food is a very, very important source of energy, which energy comes from the sun. The other forms of energy which we are interested in is something called kinetic energy. So apart from chemical energy, there is also kinetic energy. Kinetic energy is the energy which a body has because it's moving. So any particular object, as long as you're moving around, you have a certain form of energy, and that energy is what's called kinetic energy. So kinetic energy is given by half multiplied by the mass of the object multiplied by the velocity. This velocity is basically the average velocity of the object, or whatever the velocity of the object is at that particular point, the velocity of the object squared. So this is another form of energy which we are interested in, kinetic energy, the energy which an object has because of motion. So this is, like I said, there are different forms of energy. You've got chemical energy, you've got kinetic energy. The other form of energy we are interested in is something called gravitational potential energy. Now, gravitational potential energy is the energy which a body has as a result of its position in the Earth's gravitational field. Basically, this is a fancy way of saying the energy you have as a result of your height from the surface of the Earth. So the higher you are, or the further you are away from the surface of the Earth, the more energy you have, and that energy which you have as a result of your position from the surface of the Earth, that is what we call gravitational potential energy. Gravitational potential energy is given as follows. It's given by the mass of the objects multiplied by the g, which is acceleration due to gravity. This part here, mass times g, this is just the weight of the objects. Then the h is the height. So basically, this is the same as what we did, what you do when you lift an object here. When you lift an object, your S lift, how did you get your S lift? You multiplied the mass of the object multiplied by acceleration due to gravity. So the mass of the object multiplied by the acceleration due to gravity, this gives you the lift. So when you are lifting an object, you are giving that particular object a form of energy which is called gravitational potential energy. And how do you get your gravitational potential energy? You get your gravitational potential energy because lifting an object actually is performing positive work. So when you lift an object, what you are doing is you are performing work on this object by lifting it. The work you are performing is positive. So if the work is positive, this results in energy being transferred to the particular object, and that energy is the form of energy transfer as you are lifting an object is what is called gravitational potential energy. Are we clear?
Yes, clear.
Yes. If you are just if you're just pushing an object on the floor, that particular object will move with a certain velocity. So when you are pushing an object on the floor, then that object has a certain velocity with which you're pushing it. You are performing work. Again, the work you are performing on that particular object is going to be transferred to that particular object as kinetic energy. Okay? So you will see something here. One, if you are pushing an object on a horizontal surface, the positive work you are doing is transferred to that object as kinetic energy. If you lift an object from the ground, the work you are doing is going to be transferred to that object as gravitational potential energy. Okay, let's look at the last example for the day before we introduce other things which we're going to look at the next time. So here we have a 2 kg mass. So it says, example 5, a 2 kg mass falls through a distance of 4 meters. So this 2 kg mass is falling down through 2 meters, a distance of 4 meters. How much work is done on it by gravitational force? So basically, how much work does gravity do on this particular object? Because gravity is pointing down, And if this object falls through a distance of 2 meters, we can work out what the weight is, and from the weight we can find out how much work has been done. B, how much gravitational potential energy did it lose? So the first part is how much work has been done by the gravitational force. The gravitational force is just the weight of the object. So how do we get the weight of an object? The weight of an object is equal to the mass of the object multiplied by the acceleration due to gravity. The mass of the object is 2 kg, and the acceleration due to gravity on Earth is 9.8. So the weight of the object is equal to the mass of the object, 2 kg, multiplied by the acceleration due to gravity, 9.8 meters per second squared. So next here, so we get the weight as 19.6. So the weight is pointing down. The object is falling. So the object is also coming down. So in this case, you see that the work done is going to be equal to the weight of the object, then the height through which the object falls through, and the angle between the weight and the direction in which the object is falling. The object is falling down. The angle between the weight, since the weight always points down, then the displacement is down, coming down. Then you see that the angle between these two guys is equal to 0 degrees. The angle between the weight and the displacement is 0 degrees. So the work done is going to be equal to 19.6 newtons multiplied by 4 meters multiplied by the cosine of the angle, which is 0 degrees, and we get the work done to be equal to 78.6 joules. So this is how much work gravity is going to do. It's going to give these particular objects an amount of energy which is equal to 78.4 newtons. Then you work out the gravitational potential energy which has been lost. The gravitational potential energy in this case, as a result of the change in height, GPE is equal to the mass multiplied by G times height. The mass is 2 kg, the G is 9.8, then your height is 4 meters, and that gives you 78.4. So you can see that, I think this was supposed to come earlier, like that. Yeah, something like that. So you can actually see that the GPE, this one, the gravitational potential energy, has got the same size as the work which has been done. So the gravitational potential energy in this case and the work which has been done, they have got the same size. This is not a coincidence. The reason is because, in this case, as you are going to see from this work energy theorem, the work which gravity was doing is equal to the potential energy which has been lost in this case. So the lost potential energy is equals to 78.4, and the work which was done is equals to that. Are we clear? Any questions? Any questions? Okay, if there are no questions, then we'll stop here for today. We'll continue on Thursday with the work energy theorem, what is it, and also later on, after work energy theorem, we'll look at the principle of conservation of energy, and then we'll look at power. So these are things you should be able to do on Thursday. Is there a question?
I just want to ask something concerning our lecture.
Concerning a what?
Someday physics. Are you going to have a physical lecture someday, or just having online?
I have no interest in having a physical lecture with you.
Why?
COVID. You're not happy with this? Me, I'm very happy on you.
No, just I am only that also physical somehow is important.
Sorry?
Even physical somehow is important.
You are having physical classes in other classes. Are you not having physical classes? In which classes are those?
I'm having physical classes like for chemistry, math, and biology.
Yeah, that's enough.
It's enough.
Yes. What? Because the whole point really is for you to have a physical. What does a physical class looks like? You're having it there in what is in maths, chemistry, and stuff like that. With the physics department, we are particularly very, very concerned about COVID. I had COVID in January, so I know what I'm talking about. Then in that same January, early
Yeah.
February, if a workmate of us, a physics lecturer, got COVID, then he died from it.
Okay.
So we are particularly very, very concerned. We decided as a department, okay, how about if we go online fully? Can we offer this course online fully? And that's why, if you notice in our physics department, there is more commitment to offering the course online.
Okay.
The reason is because we know firsthand what COVID can do.
I was just wondering. I didn't know the reason actually.
Yes, that's basically the reason. I had COVID in January. It was very bad. I spent the whole January at home. Then at the end of that January, a friend of mine, a workmate of ours, I think he came for a meeting. So in that meeting, luckily, the meeting was also online. He got sick, so he must have got it from somewhere else. Then 1 week later, he died. So we are very touchy. Don't sorry, but there is no other way to do it. Yeah. We're very, very few. So basically, what it means is that if we get another person with COVID, then they die, work becomes very difficult. Because even right now, his death has severely disrupted the department. We are trying, but we will see. It is going to be still very difficult to recover from his loss. We have got new people, but those new people still have to be get taught. We've got 2 other new people, but they still have to learn, and it's not the same basically. Okay. Yeah. So apologies, but we are trying to do the best we can, even under the circumstances, so that you can learn. Yeah, I hope this is going to suffice. With the recorded videos and other stuff. Okay. See you on Thursday.
Okay.
Cheers.
Steve.
All right.